Mars sounds close. Until you ask the only question that really matters. How do you leave? Because landing there is not the end of the mission. It is the point where the real danger starts. The ride home has to survive dust, cold, radiation, delays, fuel problems, power problems, and a launch window that will not wait for you. And the more seriously you look at it, the more one fact becomes impossible to ignore. Mars is not just hard to reach, it is hard to stop being trapped on. If you enjoy the video, make sure to hit like and subscribe. Let's begin. Most people think landing is the big test. It is not. Landing is only the point where you stop using the speed, fuel, and support that Earth gave you. The second you are on the ground, the mission changes. Now you need to create the conditions for survival and for departure on a planet that gives you almost nothing for free. That is the first thing people get wrong. They think touchdown is the climax. It is not. Touchdown only proves that you managed to arrive. Return is a different problem. Return means the hardware has to stay alive on Mars. The power has to stay alive. The timing has to still work. The navigation has to still work. The crew has to still be healthy enough to leave. And the vehicle that goes home has to be ready after sitting for months or years in cold dust, radiation, and isolation. That is why serious Mars planning keeps getting pulled back to one issue again and again. Turn architecture. Even bringing back rocks is already forcing a very complicated chain. NASA's Mars sample return planning needs samples collected on the surface, a lander, a rocket on Mars, an orbiter waiting above Mars, and then a secure return path all the way back to Earth. That is not for astronauts. That is for sealed tubes of rock. If it takes that much to return geology, that tells you something very important right away. Getting home is not the easy half of the mission. It is the part that makes the whole mission expand. And that leads to the next point. One-way missions are much simpler. A robotic lander that never comes back can spend its mass and complexity on getting down safely and doing science. That is still difficult, but it is a contained problem. Once you demand a return, the mission grows in every direction. Now you need ascent hardware. You need propellant or machines that can make propellant. You need a longer-lasting power system. You need stronger thermal control. You need more autonomy because help from Earth is too slow. You need tighter reliability because there is no rescue. You need enough extra margin that the mission can survive a long surface stay and still leave on time. And the schedule itself becomes part of the engineering. Mars missions do not launch whenever you want. The most energy-efficient opportunities come only about once every 26 months. So return is not only a vehicle problem, it is also a calendar problem. If a system underperforms, if a power unit fails slowly, if oxygen production falls behind, if one major subsystem misses readiness, you are not necessarily slipping a few days. You can be slipping into another interplanetary cycle measured in years. On Mars, delay is not just inconvenience. Delay can become mission-threatening. Another thing people underestimate is distance. Mars feels close in fiction. In operations, it is far enough to change the entire way a mission works. The communication delay between Earth and Mars can reach more than 20 minutes one way, roughly 21 to 23 minutes under some conditions. That means a serious failure during a launch from Mars is not something Mission Control can help fix in real time. There is no live back and forth. There is no immediate correction from Earth. By the time Earth hears the problem, the event is already over. The crew or the onboard systems have to handle it there with no real-time support. Then Mars adds another layer. Sometimes the sun sits in the wrong place and communications are disrupted during solar conjunction. Signals passing too close to the sun get corrupted by interference. That means there are periods when contact is reduced or heavily limited. So even if your systems are healthy, there will still be times when the mission has to operate with far less input from Earth. That matters because return from Mars depends on timing, coordination, and trust in systems that must work with a high degree of independence. This is already visible in robotic missions. The Mars Ascent vehicle in the sample return plan is expected to be the first rocket ever launched from the surface of another planet. That should reset how people think about this problem. Humanity has launched many rockets from Earth. It has launched rockets from the Moon. Launching from Mars is different. You first have to deliver that rocket intact to the surface. Then it has to wait there. Then it has to work after long exposure to the Martian environment. Then it has to place its payload into the right orbit for the next spacecraft in the chain to find it. And that next step is not simple either. The Earth Return Orbiter has to locate a very small container orbiting Mars, match its motion, capture it, secure it, and then begin the long trip back to Earth. All of that happens with large communication delays and no live joystick control from Earth. So even for a small payload, the return is not one event. It is a sequence of tightly linked operations, each with different failure modes, each depending on the last one going right. This is why the idea that return is just the outbound trip in reverse is completely wrong. It is not reverse. It is not symmetrical. It is a separate campaign with separate hardware, separate constraints, and separate risks. On the way to Mars, the mission benefits from all the work done on Earth before launch. On the way back, the mission depends on whether a chain of systems can still function after Mars has been stressing them for a long time, and Mars is very good at stressing systems. On Earth, return is supported by industrial depth. You have launch pads, factories, technicians, fuel storage, clean rooms, spare parts, weather forecasting, transportation networks, and rescue options. A rocket leaving Earth is fresh. A rocket leaving Mars is aged. A return stack on Mars has to survive dust, cold, radiation, thermal cycling, communication delays, and launch window pressure while sitting on a planet with no global magnetic field and an atmosphere that is thin enough to be unhelpful and thick enough to still interfere with descent, ascent, dust movement, and heating. That point matters because Mars does not fail in a simple way. It does not just say no, it creates layered technical problems. The atmosphere is thin, so it does not give you the kind of aerodynamic support people are used to thinking about on Earth. But it is thick enough to generate drag, weather, heating effects, and dust transport. That means you do not get the clean simplicity of a vacuum, and you do not get the useful support of a dense atmosphere. You get the difficulties of both. The same pattern shows up across the whole mission. Mars gives you just enough of something to complicate the problem, but not enough to solve it. So the deeper truth is simple. The mission does not end when you land on Mars. That is when Mars starts testing every assumption behind the plan. It tests whether the hardware really can survive that long. It tests whether the power system can support the return chain. It tests whether the propellant plan was realistic. It tests whether the autonomy is strong enough. It tests whether your timing margins were honest. It tests whether the crew can keep the system healthy long enough to leave. And that is why returning from Mars is so hard. It is not one dramatic obstacle. It is a long chain of practical problems that all have to remain under control at the same time, far from Earth, with no fast rescue, no easy resupply, and no guarantee that a missed step can be corrected before the next launch window closes. Reaching Mars is difficult. Leaving Mars after living there is a much harsher standard. Landing only gets you to the point where that standard becomes real. The next problem is even more frustrating. Mars does have an atmosphere, but not in a way that helps you much. It is too thin to save you and too thick to ignore. Mars has an atmosphere, but it does not help the way people think it should. It is one of the most frustrating parts of the whole planet. If Mars had almost no air, some parts of the problem would actually be simpler. If it had thick air like Earth, other parts would be easier. But Mars sits in the worst middle ground. There is enough air to create drag, heating, weather and dust problems, but not enough air to make landing or launching feel manageable in the Earth's sense. That is why the atmosphere is a trap. It interferes with everything and it fully solves nothing. Start with the basic number, because this is where the scale becomes clear fast. At the surface, Mars is usually sitting at about 6 to 10 millibars of pressure. That is roughly 1% of Earth's pressure at sea level. Curiosity's early pressure readings at Gale Crater came in around 690 to 780 pascals, or 6.9 to 7.8 millibars. So when people say Mars has an atmosphere, that is true, but it is barely true in practical terms. It is not a thick blanket of air around the planet. It is a very thin layer. that is still just thick enough to get in the way, and that thin layer changes everything. It is enough to create drag during entry. It is enough to move dust across the surface. It is enough to create weather patterns and seasonal pressure changes. It is enough to cause heating during descent. But it is nowhere near dense enough to give you the kind of aerodynamic support that makes aircraft operations normal on Earth. So Mars gives you the problems that come with air, without giving you much of the help that air usually provides. That becomes even clearer when you look at what the atmosphere is made of. Mars air is about 95% carbon dioxide, with only tiny amounts of oxygen. That matters in two very direct ways. First, you cannot breathe it. There is no easy human survival value in that atmosphere. Second, any mission that wants oxygen for life support or for rocket oxidizer has to bring it from Earth or make it on Mars. The planet is giving you raw material, not a usable atmosphere. That is why NASA ran MOXIE. The idea was simple in concept and hard in reality. Mars has carbon dioxide, so maybe you can split that and make oxygen on site. That sounds like a clean solution until you look at the environment you're working with. The gas is low density, the air is cold, the pressure changes with location and season. So you are not collecting oxygen from a convenient atmosphere. You're processing a thin, weak feedstock and forcing it through machinery that has to run reliably on another planet. Every kilogram of oxygen you want has to be pulled out of a very poor source. And that leads to the next problem. Thin air does not just affect rockets, it affects flight itself in strange ways. Ingenuity showed this better than anything before it. That helicopter was operating in atmospheric densities around 0.0145 to 0.0185 kilograms per cubic meter, around 1.2 to 1.5% of Earth's sea level density. Later, as conditions changed, NASA had to push it toward even lower densities near 0.012 kilograms per cubic meter by spinning the rotors faster, around 2,700 to 2,800 revolutions per minute. That is an aircraft fighting for lift in air that is barely there. And that is the useful lesson. On a small helicopter, Mars air is too thin to provide easy lift, so the machine has to work extremely hard just to stay up. But for large spacecraft and return hardware, you run into the opposite version of the same problem. There is too little air to support ordinary aircraft-like operations, and too little air for parachutes to scale cleanly to very heavy payloads, but there is still enough air that you cannot ignore it and treat the whole thing like pure vacuum flight. Mars keeps forcing you into these hybrid problems. You cannot solve them with simple aircraft logic. And you cannot solve them with simple space-only logic either. That becomes brutal when you talk about parachutes. Robotic Mars parachutes already sound extreme when you say the numbers out loud. NASA has used parachutes about 65 feet across, around 20 meters, opening in less than half a second under loads above 30,000 pounds, after the capsule is only slowed to around Mach 2. That is already an aggressive, highly optimized system. And even then, that parachute is only part of the descent chain. It is not enough by itself. Other systems still have to finish the job. Now scale up from a robotic mission to the kind of mass people discuss for human return infrastructure. NASA's own work on supersonic retropropulsion points out that once you go above roughly 5 metric tons, new descent technology becomes necessary. Human-class payload studies push much closer to 20 metric tons. That is where the atmosphere becomes a real trap. It is thick enough that you cannot simply ignore it and do a clean vacuum-style powered descent from the start without major penalties. But it is too thin for parachutes to keep scaling usefully into those larger mass ranges. So you get forced into a very narrow and ugly technical corridor where neither parachutes nor pure propulsive landing gives you an easy answer. That is why larger Mars landing concepts keep turning towards supersonic retropropulsion. In simple terms, that means firing rocket engines while you're still moving at supersonic speed through the atmosphere. It sounds straightforward when you say it quickly. In practice, it is difficult because the rocket exhaust interacts with the incoming supersonic airflow in complicated ways. Those interactions can change forces, heating, stability, and control behavior. So to land the kind of mass you would need for a serious return mission, You first have to learn how to control a vehicle descending through an atmosphere that is thin but still dynamic enough to make the fluid behaviour messy and uncertain. And even if the atmosphere is weak compared with Earth's, Mars' weather still matters. This is another place where people get the scale wrong. The strongest Martian dust storm winds can reach around 60 miles per hour, about 97 kilometers per hour. On Earth, that number immediately sounds dangerous. On Mars, the air is so thin that those winds do not hit with the same force as a terrestrial storm of similar speed. So if you only think in terms of wind pressure, Mars sounds less threatening than it really is. But the real hazard is not the force of the wind, it is what the wind carries. Dust on Mars is persistent, fine, and damaging in slow ways. NASA describes those particles as small and slightly electrostatic, which means they cling to surfaces, coat equipment, work into moving parts, and reduce the performance of solar panels. That matters because return systems are not isolated objects sitting in perfect storage. They are part of a larger surface operation. Power systems, seals, connectors, valves, gears, radiators, sensors, and exposed surfaces all have to deal with that dust over long periods. And Mars storms can last a long time. Some cover huge regions for weeks. The rarer planet-encircling dust events happen, on average, about once every 3 Mars years. After a major storm, dust can take months to settle. That means the atmosphere does not need to destroy your return vehicle in one dramatic event. It can just slowly reduce your margins. It can make power systems weaker. It can make moving parts dirtier. It can make thermal control harder. It can make maintenance harder. And on Mars, slow damage is often worse than obvious damage, because obvious damage at least gets noticed right away. So this is the real point. Mars air is not just thin, it is strategically thin. It is thick enough to force aerodynamic design, heat shield design, weather planning, dust mitigation and descent complexity. But it is too thin to give you the easy aerodynamic benefits people instinctively expect from an atmosphere. It cannot be treated like Earth air, and it cannot be treated like empty space. That is why it keeps trapping mission design in the middle. And once you understand that, the next problem becomes unavoidable. If the atmosphere is already this awkward, then the return mission starts failing long before launch day. Because before you can ever leave Mars, you first have to land the vehicle, the fuel system, or the infrastructure that will eventually take you home. The return mission starts failing before the crew ever gets there. That is the first thing to understand. You do not land on Mars, set up camp, and then later figure out how to leave. The hardware that will take you home has to survive the entire trip in. It has to launch from Earth, survive the cruise through deep space, survive entry into Mars, survive descent through that thin and annoying atmosphere, survive landing, and then survive sitting on the surface until the day it is needed. So the problem of returning from Mars is also a problem of delivering the return system intact before the mission even begins on the ground. That is why coming home from Mars is really a landing problem hiding inside a launch problem. The rocket home is useless if you cannot get it there in working condition. And getting it there is not simple cargo delivery. It is one of the hardest transport problems in spaceflight. You're trying to put a future launch system onto the surface of another planet through an entry, descent and landing sequence that already pushes current technology hard even for much smaller robotic missions. That is where the mass problem becomes brutal. So far, the biggest payload of humanity has successfully landed on Mars is about the size of Perseverance, around 1 metric ton, roughly 2,200 pounds. That is impressive, but it is nowhere near the scale discussed for serious human return missions. Human exploration studies point more toward payloads around 20 metric tons, roughly 44,000 pounds for major surface systems. That is not a modest step up. That is not a version 2 upgrade. That is a huge jump into a different class of mission. And that gap matters because the systems that worked for a 1-ton rover do not simply stretch to 20 tons. NASA's own work says supersonic parachutes are not scalable to that mass range. So the techniques we know how to use for current Mars landings start to break down right where human-class infrastructure begins. That means the hardware you would need in order to leave Mars may belong to a mass class that current proven Mars landing systems were never designed to handle. This is where a lot of simple ideas collapse. People say, just send the ascent vehicle ahead of the crew, just pre-deploy the fuel system, just land the return hardware first. But the word "just" hides the real difficulty. Pre-deploying the ascent vehicle is not like shipping a box in advance. You are trying to land a machine that may represent a future launch pad, a future fuel depot, and the future survival of the crew all at once. If that delivery fails, the mission may be over before the astronauts even leave Earth. And all of that costs mass. Every kilogram you spend on landing safely is a kilogram you cannot spend somewhere else. That trade becomes severe very quickly. A robust Mars landing system is not a minor accessory. It is the heat shield, the aeroshell, guidance systems, navigation systems, propellant for powered descent, landing gear or touchdown systems, sensors that can still work in dust, and enough fault tolerance to survive one shot at a planet where there is no repair runway and no second attempt on the same vehicle. None of that is optional, but none of it helps you launch home directly either. It is all mass spent on surviving arrival, so descent technology steals from ascent technology. The more you spend to get the return hardware down safely, the less you have available for ascent propellant, spares, shielding, crew support, redundancy, and long-term surface operations. That is one reason Mars architecture gets so complicated. The mass you need to land is tied directly to the mass you need later for survival and departure, but the systems for landing and the systems for leaving compete with each other. Then the atmosphere makes that trade worse. Once your payload grows beyond what parachutes can realistically handle, you are pushed towards supersonic retropropulsion. In plain language, that means you start firing descent engines while the vehicle is still moving faster than the speed of sound. That is not a small step. It changes the problem completely. Now the spacecraft is not only falling through the atmosphere, it is blasting rocket exhaust into a supersonic flow around the vehicle at the same time, and that creates a fluid dynamics problem that is extremely difficult to predict and control. The exhaust plumes can interact with the surrounding airflow in ways that change the forces on the vehicle, change how stable it is, change heating and change control response. NASA has treated those interactions as a major risk area for good reason. If you are trying to land very large payloads on Mars, you're asking the spacecraft to pass through a phase where the atmosphere is thin enough to be weak, but still thick enough to make the rocket plume and airflow interact in messy and dangerous ways. So before humans can leave Mars in a serious way, engineers first have to solve how to land the amount of hardware needed for departure. And that hardware is not one neat object. It may include ascent vehicles, power systems, surface support systems, fuel production systems, storage systems, spare parts, and cargo that keeps the ascent stack alive until launch day. The bigger the mission, the more the return system turns into an entire surface infrastructure package. That is why the clean movie version is wrong. There is no single heroic spacecraft that lands, waits, launches, and comes home in one elegant arc. Mars punishes that kind of simplicity. The architecture keeps breaking apart into multiple pieces, because that is what the physics and logistics demand. You launch some things first, you pre-position cargo, you send power systems, you send ascent hardware. You may need orbiters overhead. You may need separate landers for separate functions. The more realistic the mission becomes, the less it looks like one ship, the more it looks like a network. You can already see that in robotic sample return planning. Even for a tiny sample payload, the return chain naturally splits into different elements because no single spacecraft can do every job well without becoming too risky, too heavy, or too complex. And once you move from samples to humans, all of that gets worse by orders of magnitude. More mass, more life support, more redundancy, more power, more maintenance, more failure paths. So this is the real lesson from the landing problem. Returning from Mars is not one mission. It is a linked sequence of missions pretending to be one. You need the cargo mission that lands the infrastructure. You need the surface systems that keep that infrastructure healthy. You need the crew mission that depends on all of it. and you need the ascent and orbital return chain that only works if every earlier step stayed alive long enough to hand off to the next one. And once you accept that, the next question gets even more serious. If landing the ride home already takes this much hardware, this much mass, and this much system fragmentation, then what exactly are you really sending to Mars? Not just a crew, not just a vehicle, something much bigger than that. A Mars return mission is much bigger than sending people to another planet. You're sending a whole working system that has to stay alive far from Earth. That is the scale of it. A real return mission needs a habitat, life support, power, communications, mobility, medical capability, maintenance tools, spare parts, ascent hardware, and either a huge supply of propellant or the machines that can make propellant on Mars. Once you strip away the dramatic image of astronauts stepping onto red soil, the practical reality is much harsher. You're not sending a crew with camping gear. You're sending the minimum industrial base needed to keep humans alive and create a path off the planet later. That is why Mars Return starts looking less like exploration in the normal sense, and more like building a temporary off-world outpost that can actually function. The crew cannot depend on Earth the way crews in low Earth orbit do. They cannot assume fast resupply. They cannot assume a rescue mission is coming soon. They cannot assume mission control can solve everything from the ground. That changes the entire design logic. Systems that would be support systems in near-Earth space become central systems on Mars. Maintenance stops being background work. It becomes part of survival. Power stops being a utility. It becomes the thing that decides whether oxygen can be made, whether heat can be maintained, whether communications keep working, and whether the vehicle home remains viable. That leads directly to redundancy. And redundancy on Mars is not a luxury. It becomes part of the architecture itself. On the Moon, if something goes badly wrong, rescue windows can be measured in days. On Mars, that is not the case. Resupply and evacuation are essentially unavailable on the timescales that matter during a surface mission. NASA's work on Mars autonomy and human factors treats long communication delays, minimal resupply, and lack of real-time rescue as basic realities, not edge cases. Once those conditions are accepted, every important subsystem has to be designed with backup paths, graceful degradation, and local decision-making in mind. So the return vehicle cannot be treated as one perfect machine sitting in silence, waiting for launch day. It has to be protected by the rest of the surface system. The power system protects it because without power, critical storage and production systems may fail. The habitat protects it because the crew has to stay healthy enough to maintain the whole mission. Spare parts protect it because small hardware failures elsewhere can cascade into launch failure later. Communications protect it because planning and troubleshooting still matter, even with delay. The return vehicle becomes one node inside a larger survival network. If the network starts failing, the launch system is affected even if the rocket itself looks fine. And there is another hard truth. Surface operations are not knuckle neutral. Every day on Mars consumes margin. Every EVA, every rover drive, every dust event, every temperature cycle, every compressor start, every battery discharge, every valve cycle, every repair task slowly pushes hardware toward wear and aging. On Earth, a rocket heading for launch is supported in clean facilities by large teams with tools, logistics, and controlled environments. On Mars, your clean environment is limited, your tools are limited, your parts are limited, and dust gets into everything. So the return mission is not sitting still while the crew waits. It is aging the whole time. That matters because a mission like this is not paced by human emotion. The real mission clock is mechanical and orbital. It is set by launch windows, stored propellant health, oxygen production rates, component lifetime, power margin, maintenance burden, and weather effects. A crew can feel ready to leave, but that does not matter if the systems are not ready. If a power system produced less than expected, if oxygen production lagged, if a cryogenic storage system lost too much performance, if a critical part degraded faster than planned, then psychological readiness means nothing. Mars forces the mission to run on the system's clock, and the system's clock does not care how badly the crew wants to go home. That is one of the biggest differences between Mars and places closer to Earth. On Mars, the mission becomes a negotiation between hardware lifetime and celestial mechanics. Earth and Mars line up on a schedule set by orbital dynamics, not by human preference. So if key systems underperform for months, the crew cannot simply decide to leave early or stay comfortably until a better moment. Everything has to line up. The propellant has to be ready. The power system has to still support the chain. The ascent system has to still be healthy. The crew has to still be able to operate it. The orbit overhead has to cooperate with the departure plan. The entire mission starts feeling less like a trip and more like an extended attempt to keep enough of a fragile machine alive until one narrow departure opportunity opens. This is the part many people miss when they think about Mars. They think the return trip is just the second half of the same mission. It is not. It is a second mission built out of whatever the first mission managed to preserve, produce, and not destroy. The return phase depends on the survival of the surface phase. It depends on the power the mission generated, the oxygen the mission produced, the equipment the mission kept functioning, and the crew health the mission managed to protect. In that sense, the trip home is assembled out of leftovers, outputs, and maintenance success. That is why the challenge of Mars exploration is easy to misunderstand from a distance. The hard part is not only reaching another world, the hard part is reaching another world and then becoming self-sufficient enough for a limited time to stop being trapped there. That is a much higher standard. It means you need not just transportation, but local capability. Not just a landing, but a working surface system. Not just brave people, but an engineered environment that can keep producing what departure requires. And once you frame it that way, another brutal fact comes into focus. All of this temporary civilization still depends on one thing more than almost anything else. Not morale, not courage, not even the rocket itself at first. It depends on fuel. More specifically, it depends on oxidizer. Because on Mars, the real mass problem is not just the crew or the ship. It is the enormous amount of oxygen needed to launch off the planet. The return mission stops being about astronauts the moment you look at the fuel numbers. Most people hear fuel and think of something like gasoline, methane, or some generic rocket propellant. But for Mars, the real mass problem is oxygen. Rockets need oxidizer, and they need a lot of it. NASA's MOXIE work makes this painfully clear. A human mission might need about 1 ton of oxygen for the crew to breathe over the mission. That sounds big until you compare it with launch. Just getting off Mars can demand about 25 tons of oxygen for ascent. Other NASA material puts the full propellant need around 33 to 50 tons, with liquid oxygen making up more than 75% of that mass. So when people talk about fueling the ride home, the honest picture is not just a tank of fuel, it is an oxygen supply chain. That changes the whole mission immediately. If oxygen is the biggest mass item in the ascent propellant, then bringing all of it from Earth becomes extremely expensive. Every extra ton launched from Earth drives up the entire architecture. Bigger launch vehicles, more cargo, more cost, more landing mass, more risk. This is why the return problem keeps coming back to local resource use. You do not just want oxygen production on Mars because it sounds advanced. You want it because the mission can become almost unreasonable without it. And this is where MOXIE matters. MOXIE was not a full-scale factory. It was a demonstration unit, but it did something historic. It made oxygen on Mars from the Martian atmosphere. Across its mission, it produced 122 grams total. It reached 12 grams per hour at 98% purity or better. It operated through a full Mars year. That is real progress. It moved the idea out of the category of theory and into the category of demonstrated technology. Mars gave up oxygen, and a machine on the surface proved it. But that success leads straight into a harder truth. Demonstration is not the same thing as mission closure. MOXIE worked, and that is exactly why its limitations matter so much. NASA describes a human-scale version as needing to be about 100 times larger. Other MOXIE material frames the Ascent Oxidizer challenge as about a 200 times scale-up from the demo unit's design range. That gap is the problem. The concept is not failing. The concept is working and still showing that the practical version is much larger, heavier, more power-hungry, and more demanding than the demo. So the lesson from MOXIE is not problem solved. The lesson is this is the real problem. Mars does contain the raw material you want, but the amount you need for a return mission is so large that even a successful experiment makes the scale of the challenge more obvious, not less. That is why oxygen becomes the real monster in the story. It is not enough to know how to make it. You have to make it in quantity, on schedule, with high reliability, and with enough confidence that a crew can trust it before they commit to landing. And the process itself is not gentle. MOXIE works by pulling in carbon dioxide from the Martian atmosphere, heating the system to around 800 degrees Celsius, about 1,470 degrees Fahrenheit, and then electrochemically splitting the carbon dioxide into oxygen and carbon monoxide. In one sentence, that sounds clean. In engineering terms, it means compressors, heaters, very high temperatures, durable materials, insulation, power conditioning, purity monitoring, and long-term operational stability. You are not passively collecting oxygen from a friendly environment. You're running a chemical processing plant on a cold, dusty planet with thin air and long periods of isolation. That matters because Mars does not forgive delicate industrial systems. A bad seal, a degraded heater, a dusty intake, a power interruption, or a slow leak can all become mission-level problems. On Earth, a chemical plant has maintenance teams, spare inventory, stable infrastructure, and replacement options. On Mars, every part is competing for mass budget before launch, and every repair task is being done far from resupply under harsh surface conditions. So when people say Mars has carbon dioxide, and you can make oxygen, that is true, but it leaves out the hard part. The hard part is keeping the entire production chain alive long enough to matter. Then there is storage, and storage may be just as cruel as production. Making oxygen is one challenge. Holding on to it is another. If the ascent architecture uses high-performance propellants, the oxygen likely has to be stored as a cryogenic liquid. Now the mission is dealing with boil-off, insulation, refrigeration, valves, sensors, thermal control, and long-duration losses. A return mission might need that oxygen to remain usable for months or even years after it is produced. That means the mission is not only running a chemical plant on Mars, it is also running a long-term storage system that has to stay healthy under surface conditions that are anything but stable. Mars is cold, but not in a clean, convenient way. Surface temperatures can reach around 20 degrees Celsius, about 70 degrees Fahrenheit, in favourable conditions, then plunge down toward minus 153 degrees Celsius, about minus 225 degrees Fahrenheit, in the harshest extremes. That wide range creates thermal stress everywhere. Tanks, seals, electronics, insulation systems, lines, valves, structural connections, all of them have to survive those swings. Cold by itself is not the same thing as reliable cryogenic storage. In fact, a wildly changing thermal environment can make storage harder, not easier, because control becomes more complicated. This is one of those parts of the mission that sounds boring until you realize it can decide whether anyone leaves Mars. Thermal control is not background engineering. It is mission survival. If the oxygen boils off too fast, if storage pressure management slips, if refrigeration underperforms, if valves do not behave as expected after long exposure, then the return vehicle may simply not have the oxidizer it needs. The crew could have food, shelter, and a functioning rocket structure, and still be trapped because the oxygen system did not stay inside margins. That is why fuel changes the entire shape of the mission. The question stops being, can humans physically reach Mars? That part, while difficult, is conceptually straightforward compared with what comes next. The real question becomes, can humans pre-build enough industrial capability on Mars that the ascent burn is effectively paid for before the crew ever lands? That is a much harsher requirement. It means the mission has to trust local production, local storage, local power, and long-duration system survival before the people arrive or before they depend on those systems fully. This is also why in-situ resource utilization is not some optional upgrade you add later to make the mission more elegant. It is very close to the dividing line between a Mars architecture that has a chance to close and one that collapses under its own mass. If you bring too much from Earth, the cargo burden becomes enormous. If you depend on Mars too early without reliable production, the mission becomes dangerous. So the design has to find a narrow path between launch mass and local capability, and oxygen sits right at the centre of that balance. And that is the deeper point. On Mars, fuel is not just a tank. It is infrastructure. Oxygen is not just a gas. It is a long chain of machines, power supply, storage systems, maintenance demands, thermal management, and schedule pressure. The road home is not waiting in a single vehicle. It has to be manufactured, protected, and preserved on the planet itself. That is why the return mission stops looking like an expedition and starts looking like a temporary industrial project on another world. And even after you build that oxygen chain, another problem remains. The rocket itself still has to sit there and wait. And waiting on Mars is not passive. Waiting is one more test, and Mars is very good at turning time into damage. A rocket on Earth is launched fresh. A rocket on Mars launches old. That difference changes everything. On Earth, a launch vehicle is built, tested, transported, checked, fueled, monitored by large teams, and sent up from a controlled environment. On Mars, the ascent system lands first, then sits there through cold, dust, temperature swings, radiation, and operational delays. Months can pass. In some architectures, much longer. Then after all that waiting, it is expected to work perfectly on the one day it matters most. That is why the engineering philosophy changes so much. For a Mars ascent system, peak performance is not enough. The real question is whether the hardware can still perform after Mars has been stressing it for a long time. It is not only about thrust or efficiency on paper. It is about seals, joints, electronics, sensors, control systems, structural materials, and propellant behavior after long exposure to a harsh environment. On Earth, launch vehicles are protected until close to launch. On Mars, the environment is part of the countdown for months before ignition. NASA's sample return rocket shows how stripped down this problem becomes when engineers try to make it realistic. The planned Mars ascent vehicle is only about 3 meters tall, about 10 feet, and about 0.5 meters in diameter, around 1.6 feet. Its mass is around 450 kilograms, close to 990 pounds. It uses a 2-stage solid propellant design and is expected to reach around 4 kilometers per second, about 2.5 miles per second, in roughly 10 minutes. That is not a large vehicle. It is not a flexible vehicle. It is not a comfortable multi-purpose spacecraft. It is a tightly optimized machine built for one narrow job: throw a very small payload into Mars orbit. That alone says a lot. Even the smallest honest version of a Mars launch problem turns into a highly specialized rocket. It is not elegant in the simple sense, it is severe. Every choice is driven by mass, reliability, storage, and the fact that the rocket has to wait on Mars before it is used. And if that small vehicle succeeds, it would still be the first rocket humanity has ever launched from the surface of another planet. That should make the scale of the challenge obvious. This is not a routine extension of what we already do, it is a new category of launch. The choice of solid propellant helps explain why the design becomes so constrained. Solid motors are attractive on Mars because they avoid some of the hardest parts of liquid fueling operations on another planet. You do not need a complex fueling sequence on the launch pad. You do not need pumps and transfer lines running right before launch. That removes some operational risk. But solids come with a cost. Once the motor is built and the propellant is cast, it is fixed. You do not top it off. You do not remix it. You do not tune it on launch day. It is what it is. That means storage conditions become critical. If the environment slowly changes the motor properties or narrows the performance margins, there may be little you can do about it later. This is one reason Mars ascent work has focused so much on temperature limits and storage conditions. A rocket on Mars does not need a catastrophic failure to become useless. It only needs slow erosion of margin, a little too much thermal stress, a little too much material aging, a little too much uncertainty in how the motor will behave after waiting. By launch day, the design may still look intact from the outside, but the numbers underneath may no longer close. And even if the motor works, launch from Mars is much more than ignition. It is not just thrust, it is thrust vector control, guidance, navigation, stage separation, attitude control and flight accuracy in a place with no ground crew nearby and no rapid intervention from Earth. In the sample return concept, the first stage gets the vehicle away from the surface, and the second stage shapes the trajectory so the payload reaches the right orbit. That means success is not defined by liftoff. Success is defined by reaching the correct orbital conditions for the next spacecraft in the chain to find the payload. That is a much tighter requirement than people often assume. If the vehicle launches but misses the target orbit too badly, the return chain may still fail. If timing is off, if the velocity is slightly wrong, if the orbital geometry is wrong, then the orbiter waiting above Mars may not be able to perform the rendezvous as planned. So ascent is not a single event. It is a precision delivery step inside a larger system. The engine lighting is only the start of the real requirement. And Mars gives very little forgiveness if anything goes wrong. On Earth, a scrub is painful, but it usually means lost money, lost schedule, and extra work for the team. On Mars, a scrub can mean something much worse. It can break the departure plan, consume precious margin, and in some cases push the mission toward missing a return window entirely. There is no technician team rolling out next shift to inspect a pad issue. There is no easy replacement hardware. There is no quick reset to a controlled baseline. Every anomaly is more serious because the environment is harsher, the support is weaker, and the schedule is linked to planetary motion. The communication delay makes this even more severe. Signals between Earth and Mars can take more than 20 minutes one way. So the launch logic cannot depend on real-time human supervision from Earth. It has to be deeply autonomous. The rocket and its support systems must be able to sense conditions, decide whether the launch criteria are satisfied, respond to off-nominal behavior, and continue or abort according to onboard logic. That means the ascent system is not just hardware. It is also software making irreversible decisions far from direct human control. This is one of the hardest psychological shifts in Mars mission design. People are used to thinking of rockets as machines that humans supervise closely at launch. A Mars rocket cannot work that way. It must act more like a robotic agent. It has to judge its own state, trust its own sensors, execute its own timing, and commit to a launch sequence that Earth cannot manage moment by moment. And if that sounds risky, that is because it is. The vehicle is making one of the most important decisions in the mission at the edge of human reach. So waiting on Mars is not dead time. Waiting is part of the test. The planet is using that time to attack materials, narrow margins, age systems, and expose every weakness in the design. By the time launch day comes, the question is no longer whether the rocket worked in testing on Earth. The question is whether enough of that tested behavior still survives after a long stay on Mars. And once the rocket does leave the surface, another popular assumption breaks down. Lower gravity sounds like it should make Mars launch easy. It helps, but only partly. Because Mars gives you less gravity, yes, but it also gives you an atmosphere that is too thin to help much and still thick enough to complicate the ascent. Low gravity helps, but it does not solve the launch problem. Mars' gravity is about 38% of Earth's. In simple terms, things weigh much less there. That sounds like a major advantage, and it is one. A rocket leaving Mars does not have to fight the same gravitational pull it would fight on Earth. But that is only half the story. The same planet that gives you lower gravity also gives you very little aerodynamic help. The atmosphere is too thin to provide the kind of control effects, aerodynamic shaping and flight behavior that people are used to associating with launch through air. So Mars gives you a break on gravity and then takes away many of the benefits that come with launching through a thick atmosphere. That is why low gravity does not turn Mars into an easy launch site. You're operating in a strange middle ground. The rocket is less punished by weight, but it also gets less help from the surrounding air. On Earth, dense air can be a problem because it creates drag, but it is also part of how control surfaces and atmospheric flight logic work in early flight regimes. On Mars, that support is weak. The vehicle is much closer to operating like a spacecraft almost immediately, but not completely, because the atmosphere is still there just enough to matter, and the speed requirement is still serious. NASA's Sample Return Mars Ascent Vehicle is designed to reach about 4 km per second, roughly 2.5 miles per second, in about 10 minutes in order to reach its target orbit around Mars. That is a huge amount of speed to gain in a very short time. It is not just a matter of clearing the ground and drifting upward. The vehicle has to launch, accelerate rapidly, stay stable, separate stages cleanly, and end up in a very specific orbital state. Even for a tiny payload, that is a precision event. That point matters because people often hear lower gravity and unconsciously downgrade the challenge. But orbital speed is still real. The rocket still has to perform almost perfectly. It still has to hit the right velocity and the right trajectory. And for human missions, the same problem gets worse, not better. More mass means more propellant. More propellant means bigger systems. Bigger systems mean harder landing before the launch ever happens, and the consequences of failure become life-critical. So lower gravity helps the numbers, but it does not remove the need for an extremely accurate and reliable ascent. Then Mars adds its favourite kind of difficulty. The environment is neither one thing nor the other. A rocket leaving Mars is not launching in vacuum, and it is not launching in anything like normal Earth atmosphere either. It is launching through a thin layer of gas that is weak, but still strong enough to affect the flight. That creates a guidance and a control problem in an awkward middle regime. There is too little air for normal aircraft-style logic to apply in any strong way, but there is still enough air that plume interactions, heating, attitude behaviour and aerodynamic disturbances matter. This is one of the most important patterns on Mars. The planet almost never gives you the clean version of the problem, it gives you a hybrid version. If Mars had no atmosphere, some things would be simpler. If it had thick air, other things would be more familiar. Instead, it gives you enough atmosphere to force design complexity without giving you the usual atmospheric benefits. So the ascent problem becomes part spacecraft engineering and part atmospheric engineering at the same time. That also affects guidance. As the rocket rises, control behaviour changes quickly because the air is thin and gets thinner fast while speed rises rapidly. The vehicle has to manage thrust, orientation, and stability through changing conditions without much room for error. On Earth, there are launch environments we know very well from long experience. On Mars, the combinations are less familiar and less forgiving. You're asking a vehicle to move through a flight regime that does not map neatly onto standard aircraft logic or standard vacuum space logic. And there is no fantasy version where a human pilot simply takes over and saves the day. The ascent event has to be automated because there is no other realistic option. The communication delay with Earth rules out real-time manual intervention from mission control. Signals can take more than 20 minutes one way. By the time Earth sees a problem, the launch is already over. Even in a crewed ascent vehicle, the fast control work would still depend heavily on onboard systems. Sensors, actuators, navigation logic, guidance software, and fault management are not backup layers. They are the real pilot during the critical phase. That means Mars ascent is not only limited by propulsion, it is also limited by software quality, sensor reliability, onboard decision-making, and autonomy. If the sensors drift, the control system can make the wrong corrections. If the navigation logic is weak, the vehicle can miss its target conditions. If fault management is not robust enough, a manageable anomaly can turn into a mission-ending one in seconds. On Mars, autonomous systems do not just assist the mission, they carry a large part of the mission, and even that still does not finish the job. Liftoff is only the first visible step. The public tends to treat launch as the dramatic ending, but engineers treat it as the beginning of the handoff. The rocket has to leave the surface, enter the correct orbit, and then pass the mission to the next step in the chain. That next step could be an orbiter, a rendezvous vehicle, or another spacecraft that has to be in the right place with the right fuel and the right timing. So ascent is not the finish line, it is a transfer point. That is why a successful Mars launch is more fragile than it looks. It is not enough for the rocket to fly. It has to fly accurately enough that the rest of the return architecture still works. A small error at launch can become a major problem in orbit. A slightly wrong velocity, a slightly wrong orbit, a slightly wrong time of arrival can push more burden onto the next spacecraft or break the rendezvous completely. So the escape from Mars is not one dramatic act of upward motion. It is a carefully timed chain where one moving piece has to hand off to another. This is the part that keeps raising the stakes. Leaving the surface is hard, but leaving the surface is not enough. Getting into Mars orbit is not enough either. You still have to meet something there, and around another planet, under time delay, with small targets and limited margins, that becomes its own major problem. Getting into orbit around Mars is not the same as getting home. That is another place where the mission becomes much harder than it looks from a distance. People hear launch from Mars and think that once the vehicle reaches orbit, the hard part is over. It is not. Orbit is only where the next problem starts. Now you have to meet another spacecraft or be found by one around a different planet, with long communication delays, limited propellant, and very little room for error. This is exactly why the sample return architecture is so revealing. The plan is not just launch something from Mars and send it straight back to Earth. The plan is to launch a small sealed container from the Martian surface into Mars orbit, and then have a separate orbiter find it, match its motion, capture it, secure it, and carry it home. ESA describes the challenge clearly. The orbiter has to locate a tiny capsule, move into the right orbit for rendezvous, and capture it while everything is being run across enormous distances and under long signal delays. That is not like docking with a large station in low Earth orbit. It is more like searching for a small moving object in another planet's orbital environment and then catching it cleanly, and the target is extremely small. NASA's orbiting sample container is about 0.24 meters by 0.23 meters, roughly 9.4 by 9.1 inches, with a mass of about 11 kilograms, around 24 pounds, and it can carry up to 30 sample tubes. ESA describes it as roughly basketball-sized. That means the mission is effectively saying this: launch a small sealed object from the surface of another planet into orbit, then send another spacecraft to intercept that object precisely enough that it can be brought all the way back to Earth. Once you say it in simple language, the difficulty becomes obvious. This is not a minor follow-up step. It is one of the central hard parts of the entire return chain. And even then, catching it is not enough. You do not just grab the container and head home. NASA's capture, containment, and return system is designed to do much more than simple capture. It has to orient the object properly, sterilize its exterior, and move it into a clean zone for secondary containment. That tells you something important about return missions. Even after you solve launch from Mars, even after you solve orbit insertion, and even after you solve orbital intercept, you still have another engineering layer on top of all of that. You have to protect the science and protect Earth at the same time. That changes the whole meaning of return. It is not just bring it back, it is bring it back intact, uncontaminated, and safe. For robotic samples, that means not damaging the sample, not contaminating it with material from elsewhere, and not introducing potential Martian material to Earth in an uncontrolled way. For human missions, the exact details would differ, but the logic gets even more demanding, not less. The return chain is not only about transportation, it is also about control, cleanliness, containment, and safe delivery at the far end. Then there is the timing problem. Each step in this chain depends on the previous one being accurate enough. If the ascent from Mars is slightly off, the orbit may be harder to reach or track. If the inserted orbit is wrong, the orbiter may need extra maneuvers. If tracking is less certain than expected, capture becomes harder. If the orbiter spends too much propellant correcting for earlier errors, it may lose margin for later tasks. If timing slips, the whole geometry can become worse. That is why small mistakes do not stay small for long in Mars return architecture. They can multiply across the chain. This is also why these architectures look overcomplicated to people who are not deep in the engineering. From the outside, it is easy to ask why there are so many handoffs. Why not make one vehicle do everything? Why not launch, carry, return and recover all in one system? The answer is that a single vehicle trying to do all jobs well usually becomes too heavy, too risky, or too difficult to land and operate. So the architecture breaks into parts because each part can then be optimized for a specific job, but that creates a new problem. Every handoff becomes a possible failure point. That is the trade Mars keeps forcing on mission design. A monolithic system gives you one giant point of failure. Distributed system gives you many smaller points of failure. There is no free architecture. You either accept one huge dependency or a chain of linked dependencies. Mars punishes both approaches, just in different ways, so mission design becomes an exercise in deciding which kind of vulnerability is more survivable. And this is where the phrase "coming home" starts to sound misleading. It sounds like one continuous trip, one long line from Mars back to Earth. In reality, it is a series of separate transitions: surface to orbit, orbit to capture, capture to containment, Mars escape to Earth transfer, Earth entry to recovery. Each part has different physics, different hardware, different timing constraints, and different ways to fail. The reason Mars return is so hard is not only that Mars is far away, it is that the journey back has to be broken into many precise segments, and every segment has to work well enough for the next one to still be possible. That is the deeper lesson here. Returning from Mars is not just a propulsion problem, it is a choreography problem. It is not enough to have force. You need sequence, timing, navigation, control, capture and containment, all across huge distances and with very little forgiveness. The mission is not simply moving through space. It is handing itself from one vulnerable state to another over and over without breaking the chain. And once you see that, the tension rises again. Because even if every spacecraft works, every handoff works, and every orbit works, the mission is still being held hostage by something much larger than the hardware. Earth and Mars themselves decide when the door opens, and they do not open it often. Mars does not care when you want to leave. That is one of the coldest facts in the whole mission. A lot of problems in engineering can be pushed, delayed, worked around or solved with extra effort. Mars return does not work like that. Earth and Mars line up for efficient transfer opportunities only about once every 26 months. That schedule exists whether your hardware is ready or not, whether your crew is tired or not, whether your oxygen plant is on time or not. The planets decide the rhythm first. The mission has to fit inside it. That changes the meaning of delay. In normal transportation, missing a departure might mean you leave later that day, next week, maybe next month. In Mars operations, being late can mean waiting years, not because anyone made a bad scheduling choice, but because orbital mechanics closed the door. That is why Mars return is not just a vehicle problem, it is also a timing prison. The ascent vehicle, the propellant system, the power system, the crew, the orbital assets, all of them have to be ready at the same time inside a window that is not negotiable. And missing that window is not a dramatic phrase, it is a real operational disaster. NASA's own Mars launch and assembly studies have treated missed opportunities as something that can strand major mission elements until the next cycle. For robotic missions, that is already expensive and damaging. For a crew on Mars, the stakes are much worse. If the return system is not ready in time, the result is not just budget trouble. It means longer exposure on the surface, more radiation, more wear on habitat systems, more wear on the power system, more maintenance, more food and oxygen consumed, more stress on the crew and more chances for small problems to grow into fatal ones. That is why lateness on Mars becomes existential risk. A leaking seal that would be annoying on Earth becomes much more dangerous if it forces delay. A power system that performs a little below expectation becomes much more dangerous if that slows oxygen production. A navigation issue becomes much more dangerous if the next usable departure opportunity is measured in years instead of days. Mars turns ordinary schedule slip into survival pressure. And then the mission has to deal with periods when Earth itself cannot even provide steady support. Solar conjunction is one of those moments that makes the whole thing feel even harsher. When the Sun sits between Earth and Mars in the wrong geometry, Communications are disrupted because signals passing near the sun get corrupted by interference. That means blackout periods or major communication limitations. So even if the mission is technically healthy, there will be times when the crew and the hardware are much more on their own. The mission has to survive not only the physical environment, but also the loss of normal contact. That matters more than people think. On a Mars mission, communication delay is already a serious limit. A message can take more than 20 minutes one way. Conjunction makes that even worse by reducing confidence in the connection itself. So there are periods where reassurance drops, coordination becomes harder, and the mission has to continue with less support exactly because the geometry of the solar system says so. That is another reminder that Mars Return is not running on human comfort. It is running on physics. And the ugly part is that there is no perfect mission profile that solves this cleanly. Faster trips sound better because they reduce travel time, but they usually demand more energy. More energy means harder launch conditions, more demanding trajectories, and different trade-offs across the whole architecture. Slower trips can reduce some immediate demands, but they keep the crew exposed longer and increase total mission duration, so you do not get to choose between a fast good option and a slow bad option. You choose between different kinds of pain. That is why Mars mission design often looks strange from the outside. Optimize one thing and another thing gets worse. Reduce travel time and you may increase launch mass or operational difficulty. Reduce launch energy and you may increase exposure time. Improve one safety margin and you may hurt another. There is no single clean optimum where everything gets better at once. Every Mars return profile is a compromise between mass, time, radiation exposure, launch energy, system complexity, and the limited opportunities created by orbital alignment. This is also why safe and fast do not line up in any simple way. A faster mission is not automatically safer if it demands a much more aggressive architecture. A slower mission is not automatically safer if it leaves the crew and systems under stress for far longer. Mars does not offer an easy trade. It forces you to choose which risks you can tolerate and which ones you cannot. That is part of what makes the design process so unforgiving. You're not solving a clean equation, you're balancing several dangerous limits that keep pulling against each other. And then there is the hidden part that makes all of this even more severe. By the time humans land on Mars, much of the return decision has already been made. Not emotionally, but physically. The cargo has already been launched. The ascent system may already be on the surface. The oxygen production assumptions may already be locked in. The orbital support may already be committed. The power system may already be expected to hit certain numbers. The mission does not get to land first and then calmly decide how to structure the trip home. The structure was chosen years earlier. That is the hidden horror in Mars Return. It forces commitment before proof. The crew may arrive on Mars still depending on machinery that cannot be fully validated under real conditions until it has already spent a long time on the surface. You can test components on Earth, you can simulate, you can model, you can run analogs, but some parts of the real proof only happen on Mars after the hardware has lived there, aged there and operated there. By that point, if the answer is bad, changing the plan may be impossible. So Mars Return is hard not only because the physics are difficult, but because the mission has to trust things early. It has to trust cargo manifests years ahead of use. It has to trust that landed hardware will still function after long exposure. It has to trust that oxygen production will scale enough. It has to trust that the crew will arrive into a return architecture that is truly viable, not just theoretically viable. In other words, Mars forces you to stake human lives on a chain of assumptions before the final evidence exists. That is what makes the launch window feel like a hostage situation. The crew cannot negotiate with it. The systems cannot ask for more time. The planets do not care how much money was spent or how well the mission has gone so far. Either the architecture is ready when celestial mechanics allows departure, or it is not. And if it is not, Mars keeps charging interest. More exposure, more wear, more maintenance, more risk. So the return mission is never just about one dramatic launch from the surface. It is a countdown that started years earlier. inside design decisions, cargo choices, power estimates, and production assumptions, the crew may feel like they are deciding whether to go home on launch day. In reality, the mission made that decision long before, when it chose what to trust and when to trust it. And if the mission is forced to wait, Mars keeps taking payment. Not only from the machines, but from the people. Because by the time a crew is trying to leave, Mars has already been slowly taxing their bodies, their attention, their medical resilience, and their ability to keep the whole system alive. The crew is not simply waiting for launch day. The crew is being worn down the entire time. That is one of the most important parts of a Mars return mission, because the people are not separate from the hardware. If the crew gets weaker, slower, sicker, or more mentally strained, the return system itself becomes less reliable. The people on Mars are not passengers waiting beside a rocket. They are part of the machinery that keeps the mission alive long enough to leave. Radiation is one of the clearest examples. During Curiosity's cruise to Mars, NASA measured an average galactic cosmic ray dose equivalent of about 1.8 millisieverts per day inside a spacecraft environment relevant to future human missions. On the Martian surface, Curiosity's radiation assessment detector measured about 210 micrograys per day from galactic cosmic rays, with day-night and seasonal changes affecting those numbers. These are not small background details. They tell you that both the trip to Mars and the stay on Mars keep charging a biological cost the entire time. There is no pause in the meter. Even while the mission is waiting for the right launch window, even while systems are producing oxygen or storing propellant, the crew is continuing to absorb damage. That matters because return depends on preserving enough health to leave and survive the trip back. The surface stay is not just a holding period, it is another exposure phase. Every extra month on Mars can mean more radiation dose, more strain on the bee, and more uncertainty in crew readiness. The mission is not only counting fuel and oxygen, it is counting human tolerance. Mars makes this worse by lacking one of Earth's biggest protections. Today Mars has no global magnetic field. Some regions of the crust still carry old magnetization, but there is no planet-wide magnetic shield like Earth's. That means there is no broad planetary defense helping reduce radiation exposure the way Earth does. Mars offers some atmospheric shielding, but the atmosphere is thin and it is not enough to solve the problem, especially for high-energy cosmic rays and major solar events. So the mission is not only limited by distance, it is limited by how long humans can stay exposed before the biological cost becomes too high. That is a huge difference from the way many people casually think about another planet. Mars is not just far away, it is an environment where the protective systems Earth gives us by default are mostly gone. On Earth, a human body lives under a thick atmosphere and a global magnetic shield. On Mars, the crew lives with a thinner protective layer and much less planetary help, so exposure becomes part of the return equation. It is not just about whether the rocket is ready, it is about whether the people who must launch it are still fit enough to do so. Then there is temperature, and Mars is severe there too. The median surface temperature is around minus 65 degrees Celsius, about minus 85 degrees Fahrenheit, but the real range is much wider. In warmer conditions, surface temperatures can climb into the 20s Celsius, around the 70s Fahrenheit. In the harshest conditions, they can fall toward minus 153 degrees Celsius, around minus 225 degrees Fahrenheit. NASA has even pointed out that near the equator at noon, it could feel like spring at your feet and winter at your head because the thin air loses heat so quickly. That kind of environment does not just make daily life unpleasant, it attacks both people and machines at the same time. For hardware, wide thermal swings mean material fatigue, seal stress, battery performance issues, electronic stress, and more difficult condensation control. For humans, it means harder EVA planning, more thermal risk, more dependence on suits and habitat systems, and more operational effort just to do ordinary work safely. Every one of those effects feeds back into mission reliability. If thermal stress hurts the equipment, maintenance burden rises. If thermal conditions complicate human operations, crew fatigue rises. Both paths make the return mission harder. That is one reason Mars missions become so tightly interconnected. Human health, habitat integrity, equipment performance, and launch readiness are all tied together. A thermal issue is not just a thermal issue. It might also be a maintenance issue, a battery issue, an EVA issue, and eventually a launch issue. Mars keeps turning separate categories into one linked system. Distance from Earth makes medicine more difficult too. NASA's human systems work keeps stressing the same basic reality. Long communication delays, little to no resupply, and no realistic evacuation change the whole structure of operations. On missions near Earth, a lot of medical, technical, and procedural support comes from larger teams on the ground. On Mars, a small crew has to handle much more on its own. That means a medical problem before launch is not just a private health issue. It becomes a mission systems problem immediately. If one crew member is injured, sick, or cognitively degraded, that can affect maintenance workload, EVA capability, monitoring, repair tasks, emergency response, and even the basic staffing needed to prepare for departure. Fewer healthy hands means fewer people available to support the machinery that produces oxygen, protects propellant, checks systems, and gets the ascent sequence ready. On Mars, aerospace risk and medical risk merge together. A crew health problem can become a launch risk, and a launch delay can become a crew health problem. They stop being separate categories. That same coupling shows up in morale and mental performance. A Mars crew would live with delayed conversations, long periods of autonomy, dust contamination, confinement, power worries, maintenance pressure, and the knowledge that the way home depends on machinery they cannot fully trust until it works. That is not just an emotional issue. It affects the quality of the mission directly. Stress can increase error rates. Fatigue can hurt judgment. Poor sleep can damage decision-making. Tension inside a small crew can reduce coordination. And on Mars, small drops in human performance matter, because there is so little margin and so little backup. This is why the psychological side of the mission cannot be treated as atmosphere or flavour. It has operational value. A crew under continuous pressure may maintain systems less effectively. They may miss early signs of degradation. They may communicate less clearly. They may respond more slowly during anomalies. On Earth, those effects are serious. On Mars, they can stack with technical problems in dangerous ways because there is no fast rescue and no large support team nearby to absorb mistakes. So when people picture a crew waiting on Mars for the day they leave, the honest picture is much harder. They are not resting beside a rocket. They are being taxed every day by radiation, temperature, confinement, delay, maintenance burden, and uncertainty. And all of that is happening while they still need to preserve enough physical and mental capacity to execute one of the most demanding departures humans would ever attempt. That is why Mars is hard to leave. By the time launch day comes, the planet has already been working on the crew for months, maybe longer. It has been charging the body, narrowing margins, adding wear, and forcing the humans at the centre of the mission to keep functioning under conditions that would already be difficult even without a launch ahead of them. And underneath all of that, another quiet dependency is still deciding whether the return mission lives or dies. The rocket may leave only once, the crew may get only one good window, but long before either of those things, there has to be power. Because without power, none of the oxygen system, life support systems, storage systems, or navigation systems ever stay alive long enough to matter. Power decides whether the return mission is real long before the rocket ever leaves the ground. That is easy to miss because rockets get the attention and power systems do not. But on Mars, electricity is what keeps the return chain alive. No power means no oxygen production. No power means no cryogenic control. No power means weaker communications, weaker computing, weaker maintenance capability, weaker mobility, weaker life support. And once oxygen production fails or storage fails, the launch fails with it. So the ascent vehicle is not only powered on launch day, it is being powered for months before ignition by the system that keeps the whole surface infrastructure running. That is why Mars return is really a rocket problem with a power problem underneath it. A MOXIE-style oxygen plant is not a passive device. It needs compression, heating, electrochemistry, monitoring and control. Scale that up to human mission levels and the power demand rises fast. Then add habitat systems, environmental control, computing, communications, tools, rovers, maintenance gear, storage systems, sensors, and whatever cooling or thermal regulation the mission needs. The return architecture starts to look less like one rocket waiting in the cold and more like a power network trying to keep a whole chain of critical systems above failure. And that leads straight into the first big trap. Solar power sounds clean, simple, and attractive. Mars gets sunlight. Solar arrays are proven. At first glance, it sounds like a reasonable match, but that logic gets weaker the moment dust enters the picture. NASA's Mars dust work is very clear about the danger. The dust sticks to surfaces, works into machinery, and is especially bad for solar panels because even modest dust events can reduce the sunlight reaching the arrays. That means a solar-powered return mission is never just a matter of calculating output on a clean day and writing down a number. The real problem is not peak power on a perfect afternoon. The real problem is degraded power on a bad week, in a dusty season, with a tired system, while the launch schedule keeps moving. Once you think about it that way, solar stops looking like a single subsystem and starts looking like a long list of dependencies. You need a degradation model, you need cleaning strategies, you need battery support, you need storm planning, you need margin for seasonal variation. You need to know how much uncertainty the rest of the mission can tolerate if the arrays slowly lose effectiveness. And Mars does not need to wipe out your solar farm to put the mission at risk. It only needs to reduce output enough for long enough that the rest of the schedule starts slipping. That is the dangerous part. If oxygen production drops below the required pace, the impact may not look dramatic at first. If battery recharge gets weaker, if overnight reserves tighten, if thermal control has to be rationed more carefully, if communication cycles get cut back, the mission may keep functioning in a reduced state for a while. But Mars return is a chain, and a chain can fail slowly before it fails openly. Solar panels do not have to die, they just have to become mediocre for long enough. That is one reason nuclear power keeps coming back into serious Mars mission discussions. The case for it is obvious. Nuclear systems are much less dependent on sunlight, seasonal daylight, dust opacity, and storm conditions. They can provide stable output through the times when solar is most vulnerable. On a world where power continuity affects oxygen production, storage, life support, and launch readiness, that stability is extremely valuable. It weakens one of the biggest environmental threats in the mission. But nuclear systems do not magically simplify Mars. They solve one major problem and introduce others. They add mass, they create heat rejection challenges, they increase integration complexity, they raise launch safety concerns before the mission even leaves Earth. They also create new failure consequences if something goes wrong. This is the same pattern Mars keeps forcing on engineers. The better option is often better only because it removes one dominant risk while introducing a set of quieter and more technical risks that are harder to explain in a simple way. So there is no clean answer here either. Solar power is lighter in some ways and operationally attractive, but dust and seasonal uncertainty can damage confidence in the whole return chain. Nuclear power improves continuity, but it adds system complexity, thermal management demands, and different engineering burdens. Mars does not let you choose between easy and hard. It makes you choose between different categories of hard, and even that is still incomplete. Because generation is only half the issue. Storage matters just as much. A Mars day is about 24.6 hours, close enough to Earth's day that people sometimes underestimate how difficult the power profile still is. The issue is not the length of the day by itself. The issue is what happens across night cycles, dust events, seasonal shifts, maintenance periods, and emergency operations. If power is generated unevenly or interrupted, the mission needs stored energy to bridge the gap. That makes batteries and storage systems part of the return engine whether people notice them or not. Every kilowatt hour that cannot be buffered becomes a future task that may not happen on time. Oxygen production cannot simply shrug and pause forever. Cryogenic management cannot ignore outages for free. Communications cannot stay high-duty cycle when power margin collapses. Computing and navigation cannot be treated as optional if the mission is protecting a launch chain. In that sense, stored energy is delayed thrust. It is power saved now so the mission can still perform the work that makes departure possible later. That changes how you think about the rocket itself. The rocket does not just need fuel in a tank, it needs a long prehistory of successful energy management. If the power system underperforms for weeks, the oxygen plant may produce too little. If storage is weak, night operations may be cut back or critical systems may be cycled too aggressively. If dust reduces input and the batteries are not large enough, the mission can enter a constant state of catch-up. And catch-up is dangerous on Mars because the launch window does not move to help you. So when people ask whether Mars return is mainly a propulsion challenge, the answer is incomplete. Propulsion matters, but power decides whether propulsion ever becomes available. That is the hidden hierarchy. Engines matter on the day you leave. Power matters every day before that. Power determines whether oxygen gets made, whether it stays stored, whether life support keeps the crew capable, whether communications and navigation remain trustworthy, whether tools still work, whether maintenance keeps up, and whether the launch chain reaches readiness before orbital timing runs out. This is also why the power system can quietly become the mission's vote on whether the crew gets home. It does not get the cinematic attention. It is not the dramatic launch shot, but it is the system that decides whether the mission can keep all the other systems alive long enough. A weak propulsion system is obvious. A weak power system may take months to reveal how much damage it has already done. That makes it in some ways more dangerous. It can drain readiness without creating one single event people can point to, and that is one of the hardest truths about Mars. The rocket home may be decided by something that looks at first like a utility subsystem, not by one spectacular failure, but by a slow shortfall in available energy that weakens oxygen production, storage, maintenance, and crew operations until the launch is no longer viable on schedule. Mars keeps moving the centre of the problem away from the dramatic hardware and into the quiet systems that support it. But even with enough power, the mission still has to survive another enemy that does damage in slow, ugly ways. Because once you build machines on Mars, Mars starts aging them. Dust, temperature swings, limited spares, and constant wear turn maintenance into a fight that never really stops. And that means the next threat to getting home is not a single explosion or a giant storm. It is entropy, one small failure at a time. Mars does not have to destroy your mission in one big event. It can wear it down piece by piece. That is what makes maintenance on Mars so dangerous. People usually picture failure as something dramatic, an explosion, a crash, a major rupture. But for a Mars return mission, the more likely threat is slow damage, small losses, small contamination, small drift in performance, small cracks in reliability. The return system does not have to be blown apart to fail, it only has to be pushed out of margin. Dust is one of the clearest examples. On Mars, dust is not just background weather. It is a constant operational problem. NASA describes Martian dust as very fine, slightly electrostatic, and prone to sticking to surfaces. That means it does not simply blow past your hardware. It clings to it. It coats equipment. It gets into moving parts. It works its way into places where mechanical systems need to stay clean and predictable. And that matters because the return mission is not one sealed object sitting untouched on the surface. It is a whole network of systems. Pumps, valves, seals, hatches, cables, actuators, radiators, solar arrays, suits, connectors, tools, storage lines, and electronic interfaces. So dust does not need one dramatic sabotage moment. It just needs time. If it gets into a bearing, the bearing wears faster. If it coats a seal, the seal may not behave the same way. If it builds up on a panel or radiator, performance drops. If it contaminates connectors, troubleshooting gets harder. That is the real pattern on Mars. Damage accumulates. The environment keeps applying pressure to the same systems day after day until something important is no longer operating where it should. Temperature cycles make that worse. On Earth, critical launch hardware spends most of its life in controlled settings until the day it flies. On Mars, systems sit outside or in harsh surface conditions and go through repeated thermal swings for long periods. Materials expand and contract. Metals move, lubricants change behavior. Seals harden, creep, or lose their ideal properties. Electronics face harder transitions between warm and cold. Thermal interfaces that looked fine in testing can become more uncertain over time. In that kind of environment, aging is not something you treat as a background number in a report. It is part of everyday operations. That is one of the harshest differences between Mars and Earth. On Earth, engineers fight to reduce pre-launch uncertainty. On Mars, the environment keeps adding uncertainty after landing. The mission is not protecting fresh hardware until launch day. It is protecting aging hardware and hoping to preserve enough performance that launch day remains possible. And then there is the spare parts problem. Every spare you send to Mars costs mass. Every kilogram of spare hardware competes against food, shielding, science equipment, mobility system, life support, propellant-related systems, and all the other things the mission also needs. That means maintenance strategy is not just bring extra stuff. It is a series of hard choices about what you think is likely to fail and what you're willing to risk. Bring too little and a failed pump, damaged cable, cracked connector, or stuck valve can become mission-ending. Bring too much, and the whole outbound architecture grows heavier and more difficult to close. This is why maintenance planning on Mars becomes a confrontation with probability. You are deciding in advance which failures deserve protection and which failures you are gambling against. That is a brutal way to design a mission, but Mars forces it. You cannot carry a full warehouse. You cannot carry Earth's supply chain with you. So every spare is an argument about risk, and some of those arguments will be wrong. That also changes what repair means. On Mars, repair cannot depend on quick expert intervention from Earth. The communication delay makes even normal troubleshooting slower and more difficult. Earth can still advise, but the crew has to do much more of the direct observing, isolating, and acting on their own. NASA's human systems work keeps coming back to this point. Mars missions demand stronger crew autonomy and stronger system autonomy. In practical terms, that means the people on Mars are not only explorers, they are mechanics, operators, medics, technicians, inspectors, and a local version of mission control all at once. That is a big burden. It means the crew has to diagnose issues with limited tools, limited parts, limited time, and under environmental stress. It means procedures have to be good enough to work without immediate ground correction. It means systems must be designed for maintainability, not just performance. And it means the mission depends on a small group of people continuing to function across many different roles for a long time. If any one of those roles starts to break down, the return chain can start breaking with it. This is another place where Mars makes simple ideas collapse. People say if something breaks, repair it. But repair on Mars is not just a task, it is its own mission layer. First you need to notice the problem, then you need to identify the cause correctly, then you need to know whether the issue is urgent, whether operating in degraded mode is safe, whether the right part exists, whether the crew has the time and physical abilities to do the repair, whether doing the repair exposes them to other risks, and whether fixing one problem creates stress somewhere else. Even with good procedures, that is hard. Under delay, dust, fatigue, and time pressure, it gets much harder. And this is where the real terror of Mars maintenance becomes clear. The launch from Mars may not be cancelled by one giant visible failure. It may be cancelled by something small. A seal that degrades a little too far, a dusty bearing that starts adding drag, a compressor that delivers a bit less than it should, a thermal control loop that no longer holds tight enough margins, a guidance sensor that drifts slowly over time. On Earth, those might be maintenance tickets. On Mars, those are threads in a net that can trap the whole mission. That is why the return problem is so difficult to explain in one sentence. It is not that Mars demands one impossible machine. It demands many difficult machines that all have to remain good enough at the same time. The oxygen system has to stay good enough. The storage system has to stay good enough. The power system has to stay good enough. The habitat has to stay good enough. The crew has to stay good enough. The ascent vehicle has to stay good enough. The communications and navigation chain has to stay good enough. And maintenance is the process that tries to hold all of that above failure while Mars keeps pulling downward. So maintenance on Mars is not routine support work. It is a running battle against entropy. Every day the crew is trying to stop the mission from becoming slightly worse than it was yesterday. Sometimes they win by a lot. Sometimes they only slow the loss. But the pressure never stops. Dust keeps settling. Materials keep aging. Margins keep being consumed. Spares keep being finite. Human attention keeps being limited. And the launch window keeps getting closer. That is the deeper reason Mars is so hard to leave. The mission is not waiting in a stable state for the day of departure. It is fighting to remain launch capable, while the environment keeps trying to make that impossible in small, boring, dangerous ways. And if enough of those small problems line up, the mission fails without ever producing the kind of dramatic scene people expect. But even if the crew wins that fight, even if the ascent works, the rendezvous works, the containment works, and the spacecraft starts coming back toward Earth, the danger still is not over, because Earth is not waiting passively at the end. At Mars return speeds, home becomes another violent engineering problem. Escaping Mars does not mean the mission is over. It means you have traded one set of dangers for another. By the time a spacecraft comes back to Earth from Mars, it is carrying enormous kinetic energy. That energy has to go somewhere. Most of it goes into the atmosphere as heat, stress, and deceleration. So the final step is not a calm arrival. It is one more extreme engineering event. And if that event goes wrong, everything that happened before it can still be lost. That is why returning to Earth from Mars is re-entry on hard mode. NASA's sample return studies put Earth entry speed at roughly 11 to 12 kilometers per second, around 6.8 to 7.5 miles per second. Those numbers are much higher than what people usually associate with spacecraft coming back from low Earth orbit. And the first part of entry is especially violent. The heating can become intense in the first minute, and the capsule design NASA studied had deceleration loads of about 40 to 80 G. That is not just a fast trip home. It is a severe atmospheric event where thermal protection, structural integrity, and stability all have to hold together at once. The important point is that Earth's atmosphere is not automatically your friend just because you're home. At Mars return speeds, the atmosphere becomes another hard boundary condition. Enter too aggressively, and the heat and deceleration can become overwhelming. Enter too shallow and you can create different problems with stability, control, or the overall entry path. So the final return to Earth becomes one more place where the mission is being judged by physics with very little forgiveness. For human missions, the same basic problem gets even tighter. Older NASA Mars architecture work has cited Earth direct entry limits around 13 kilometers per second, around 8 miles per second for optimized human returns. Even if future crewed mission designs use different profiles or different ways to manage entry, the message stays the same. Coming back from Mars means arriving at Earth much faster and with much more energy than the kinds of returns people are used to hearing about from low Earth orbit. That makes the heat shield, the guidance profile, the structure, and the deceleration plan central to survival. So Mars does not let you relax once you leave the planet. It gives you one last major test at the place everyone assumes is safe. Earth is safe for ordinary life. It is not automatically safe for a vehicle arriving from interplanetary space at extreme speed. The energy of that trip has to be handled with precision. If it is not, the final environment can destroy the mission just as effectively as Mars could. And in robotic sample return, there is another layer on top of pure survival. The capsule does not only need to survive entry, it has to preserve what is inside and protect Earth at the same time. NASA's sample entry work looks closely at loads, temperatures, winds at impact, and structural integrity because the sample canister must not rupture even if the recovery scenario is harsh. More recent capture and containment planning adds even more requirements, including exterior sterilization and secondary containment before delivery. That means the mission is not simply trying to land safely, It is trying to land safely while preserving scientific integrity and respecting planetary protection all the way through recovery. That changes the nature of the final descent. The goal is not only to keep the capsule intact enough to recover, the goal is to keep the entire chain of science and biosafety intact too. If the sample is damaged, contaminated, or released in the wrong way, then the mission has failed in a deeper sense, even if the vehicle technically made it back. So the last step home is still part of the return architecture, not a cleanup phase after it. For a future human mission, the exact containment rules would differ from a robotic sample capsule, but the broader lesson becomes even more important. A Mars mission does not end at Earth approach. It ends only when the arrival is controlled, safe, and usable. Crew health, vehicle integrity, landing accuracy, post-landing recovery, and whatever quarantine or biological controls are required would all become part of the same final system. That means getting back to Earth is still not the endpoint in the operational sense. It is another threshold the mission has to cross without losing control, and at these speeds, guidance errors become more dangerous. The atmosphere is not forgiving when you arrive from Mars. Entry angle, thermal load, aerodynamic stability, deceleration, parachute logic if any is used, terminal descent behaviour, and landing conditions all interact. NASA's sample return studies show this clearly in the trade between minimising heating and preserving stable behaviour lower in the atmosphere. Reduce one problem too aggressively and you can make another one worse. That means Earth at the very end is still a precision engineering challenge. This is important because people often picture Earth return as the easy half once the deep space travel is over, but Mars return speed compresses margin. Small errors can have large effects. A slightly wrong entry condition can shift heating, deceleration, and stability together. A slightly wrong structural assumption can matter more because the loads are so high. A slightly wrong recovery condition can matter more because the capsule may have gone through an unusually violent atmospheric event. So the destination everyone thinks of as safety is still acting like a demanding physical system right up to touchdown. That is the final escalation in the Mars return story. The mission is not complete at trans-Earth injection. It is not complete when the spacecraft leaves Mars behind. It is not complete at Earth approach. It is not complete when the heat shield starts glowing. It is not complete even at parachute deploy if parachutes are part of the architecture. It is complete only when the crew or payload is recovered safely, contained correctly, and confirmed to be intact in the way the mission required. That is what makes the whole return chain feel so severe. There is no soft ending built into it. Every phase keeps demanding high performance all the way to the end, because the energy and complexity of interplanetary travel have to be paid off somewhere. The heat does not care that the hard work was already done on Mars. The atmosphere does not care that the spacecraft survived launch from another planet. The final arrival still has to be engineered, managed, and survived with the same level of seriousness as everything before it. So even home becomes part of the Mars mission. Earth is not just where the story ends, it is the place where the last test happens, and that is a useful warning because it shows the full shape of the problem. Returning from Mars is not one giant obstacle followed by a safe glide back. It is a long chain of exacting transitions, and the last one can still undo all the rest if it is treated casually. And that is why the robotic sample return effort matters so much. It is the clearest warning humanity has so far. If bringing back a small set of rock tubes already requires this much architecture, this much containment, this much orbital precision, and this much care at Earth arrival, then bringing back humans is not just a larger version of the same mission. It is a much steeper problem. Mars sample return is not a side story. It is the clearest warning we have about what Mars really demands from a return mission. People sometimes talk about bringing astronauts home from Mars as if it is just a bigger version of robotic exploration. But if you want to see how hard return really is, look at what it takes just to bring back a few sealed tubes of rock. That is the honest baseline. The current sample return concept already forms a long and unforgiving chain. Perseverance collects and stores the samples. A future system has to get those samples off the surface. A Mars ascent vehicle has to launch them into orbit around Mars. Then an Earth return orbiter has to find that object in Mars orbit, capture it, secure it, and carry it back to Earth. The orbiting container itself is tiny, about 11 kilograms, around 24 pounds, and it can carry up to 30 tubes. That is not a crew cabin. It is not life support. It is not a pressurized ascent stage full of people. It is a small payload. And even for that small payload, the architecture already includes surface collection, launch from another planet, orbital rendezvous, secure containment, interplanetary transfer, and high-speed Earth return. That should reset the entire conversation. If bringing back a payload roughly the size of a basketball already forces this much structure, this much precision, and this many linked systems, then crewed return is not just more of the same, it is much worse. It is worse in mass, worse in reliability demands, worse in life support, worse in power, worse in timing, worse in everything that already makes sample return difficult. Sample return is not a side challenge on the road to human Mars missions. It is the small, honest version of the same problem. And the mission has already shown how quickly Mars architecture grows until reality pushes back. ESA has noted that in 2024 NASA moved to update Mars sample return in order to reduce complexity, risk and cost, while ESA continued validating the Earth return orbiter against alternative architectures. That detail matters because it proves something important. The difficulty is not the theoretical overthinking. The agencies doing the work are having to revise the mission because the original version was too complex, too risky, or too expensive in the form first imagined. That is exactly the lesson a Mars return mission keeps teaching. The architecture expands because reality keeps demanding another layer. You need a lander, then you need a rocket on Mars, then you need an orbiter, then you need capture and containment, then you need Earth entry, then you need recovery rules. The chain keeps growing until the cost, mass, or risk becomes too large, and then the design has to be pulled back and reshaped. That is not a sign that Mars exploration is impossible. It is a sign that Mars punishes simplified plans. And that kind of redesign should not be misread as failure. In Mars mission work, redesign is often measurement. It is what happens when the concept finally meets enough real engineering detail that vague confidence stops surviving. A mission that has to launch the first rocket from another planet, execute autonomous orbital capture around Mars, preserve sample integrity, and meet planetary protection requirements on Earth was never going to remain a clean diagram forever. The point is not to preserve a neat concept. The point is to discover what the real mission actually costs in mass, complexity, autonomy, and risk. That is one reason sample return matters so much beyond the science itself. Yes, the samples are valuable. Yes, bringing Mars material back to Earth matters scientifically, but the mission is also exposing the hidden layers of the return problem before humans are inside that architecture. It is showing, with real engineering consequences, where the bottlenecks are. It is forcing mission planners to face all the ugly transitions that a human mission would face too, only with far less tolerance for failure. And robotic Mars missions are already giving us numbers instead of guesses. MOXIE gave real oxygen production data on Mars. Ingenuity gave real data on atmospheric density and what powered flight looks like in that environment. Curiosity gave radiation data during cruise and on the surface, along with pressure measurements and environmental variability. Dust storm observations gave real information about frequency, scale, and persistence. These missions are doing something very important for the broader Mars question. They are replacing romantic assumptions with measured constraints. That is why the conversation is more serious now than it was a generation ago. We are not only talking in concept art anymore. We have pressure numbers, radiation numbers, density numbers, oxygen production numbers, dust behavior, thermal conditions, surface variability. Those numbers do not make Mars less interesting. They make it less forgiving. They strip away the comfortable idea that boldness alone will carry the mission. They show where the real limits are. And the warning coming out of all of this is simple. If it is this hard to bring back geology, then bringing back biology would be harder. If it is this hard to bring back a small sealed payload with no life support, no crew health, no crew psychology, and no need to keep humans alive during the return chain. Then bringing back astronauts is harder still by a very large margin. Sample return is not the full Mars return problem, but it is close enough to expose the shape of that problem in honest detail. That is why it deserves to be taken seriously as a warning shot. It is the smallest realistic return architecture, and even at that scale, the mission becomes a chain of difficult operations with very little slack. Launch from Mars is hard. Orbital capture is hard, containment is hard, Earth return is hard, and once you stack those together, you start seeing the deeper truth. Landing on Mars was never the moment where the challenge ended. It was only the point where the next, harder chain began. That is the fantasy sample return destroys. A lot of people still carry the idea that once we solve landing, the rest is just engineering scale-up. But sample return shows that landing only buys you the right to start the real argument with the planet. You still have to survive the surface, you still have to preserve the launch system, you still have to get into orbit accurately, you still have to rendezvous, you still have to contain what you brought back, you still have to survive Earth arrival. Landing is not the solved half, it is the entrance fee, and that is why Mars sample return matters far beyond its own science goals. It is not only about rocks, it is about forcing honesty into the Mars conversation. It shows that the return architecture is where confidence gets tested. It shows that the trip home is not a line drawn backward from the trip out. It is a separate engineering campaign with its own demands, its own failure paths, and its own way of growing until reality pushes back. So the warning is not subtle. If a mission this small is this hard, then a crude Mars return is not a matter of adding a few bigger systems to a familiar template. It is a much steeper climb, more mass, more dependence on local infrastructure, more health risk, more autonomy, more maintenance, more stored propellant, more power, more ways for timing to break, more ways for one weak subsystem to poison the whole chain, and that brings everything together. The real reason returning from Mars is so hard is not any one problem by itself. It is that every time you solve one major problem, you create a new dependency that also has to survive. The hardest truth about returning from Mars is that the problems do not line up one after another in a neat list. They branch. You solve one, and instead of getting closest to the end, you expose two more that now matter just as much. That is why Mars return feels so difficult even when progress is real. It is not because nothing works. It is because every working solution creates a new dependency that also has to work, and keep working, and stay inside margin at the same time. Start with propellant. You can make oxygen on Mars. That is a real breakthrough. MOXIE proved the idea. So at first that sounds like a huge piece of the puzzle falling into place. But the moment you say, yes, we can make oxygen there, the next set of demands arrives immediately. Now you need compressors to pull in that thin carbon dioxide atmosphere. You need heaters that run at very high temperatures. You need electrochemical hardware that stays reliable. You need scaling far beyond a small demo unit. You need purity control, you need storage, you need thermal management. You need valves, sensors, insulation, and long-term electrical support. So the solution is real, but it is not self-contained. It opens a bigger system. Then look at power. Fine, you build the power system needed to support oxygen production. Now that power system becomes another dependency. If it is solar, you inherit dust, reduced panel performance, night storage problems, seasonal uncertainty, cleaning challenges, and the risk that mediocre output for too long can break your schedule. If it is nuclear, you reduce some of those risks, but you add mass, heat rejection problems, integration issues, and different failure modes. So power solves one problem and creates a new one. Then if you solve dust with redundancy or cleaning hardware, you inherit mass penalties. Extra hardware means more cargo, more landing mass, more maintenance, and more complexity. This is the pattern everywhere. Progress on Mars is not additive, it is branching. The same thing happens with ascent. You can build a rocket that leaves Mars. Good. That sounds like the central problem, but the moment that is solved, the next dependency takes over. Now the rocket has to reach the right orbit at the right time with the right guidance accuracy so that next spacecraft can meet it. That means ascent is not just propulsion, it becomes timing, navigation, autonomy, and orbital precision. Then even if rendezvous works, you are not done. Now you inherit capture, then containment, then secure transfer, then Earth return, then Earth re-entry. Mars never gives you a clean final boss. It gives you a chain of nested final bosses. That is why the mission can feel cursed to designers. Every success moves the next impossibility into view. Solve landing, and now surface survival becomes the issue. Solve surface survival, and now propellant becomes the issue. Solve propellant, and now storage becomes the issue. Solve storage, and now long-term maintenance becomes the issue. Solve ascent, and now rendezvous becomes the issue. Solve rendezvous, and now Earth entry becomes the issue. The mission keeps refusing to collapse into one central problem because Mars return is not one central problem. It is a structure of linked dependencies, and all of them have to remain alive together. The same thing is true with humans. You can shield radiation better. You can train the crew for higher autonomy. You can pre-position supplies. You can improve habitat systems. All of that helps, but it does not remove the next dependency. It only gets you far enough to feel it more clearly. A healthier, more capable crew is still trapped inside launch windows they cannot control. A better habitat is still operating under conjunction blackouts and communication delay. Better survival systems do not erase the aging of the power system or the oxygen plant or the ascent vehicle. Human capability does not cancel Mars timing. It just means the crew can stay alive long enough to experience the full force of that timing. That is one of the most brutal parts of the whole mission. Endurance is not freedom. On Mars, endurance can become another dependency. If the crew can survive longer, that helps. But it also means the architecture may quietly come to depend on longer waiting, longer maintenance, longer exposure, and more system aging. The mission turns survival into a way of buying time. But time on Mars is not neutral. Time means dust, radiation, fatigue, thermal cycles, drift, and more chances for something small to become decisive. This is also why the Moon, as useful as it is not a full rehearsal for Mars return. The Moon matters a lot, is the right place to learn discipline, procedures, operations, hardware integration, surface work, and many other things. But it does not reproduce the full Mars stack. It does not give you months-long interplanetary transit. It does not give you 20-plus minute communication delays. It does not give you rare launch windows with years between the best opportunities. It does not give you a meaningful atmosphere that is too thin to help and too thick to ignore. It does not give you the same level of dust persistence interacting with a longer and more isolated return chain. And it does not force you in the same way to think about local oxygen production as a serious part of getting home. That difference is not small. Lunar missions teach systems discipline. Mars demands systems independence. On the Moon, Earth is close enough that rescue, resupply, and tight operational supports still shape the architecture in a big way. On Mars, the mission has to stand on its own much more completely. That is a different standard. It means the crew, the machines, and the local infrastructure have to absorb problems that would still be exported back to Earth in a lunar mission. The Moon is a critical step, but it does not fully simulate the way Mars forces a mission to become its own little world. And that is exactly why a successful return from Mars would mean so much. If humans ever leave Mars and come back safely, the achievement will not be that we built a bigger rocket. That description is much too small. It will mean we learned how to move a functioning slice of civilization across interplanetary space, keep it alive on a hostile planet, produce critical resources there, preserve the systems needed for departure, launch from another world, navigate in orbit around it, and then survive the return to Earth at interplanetary speeds. That's a very different level of capability. It would mean humans learn not just to visit another world, but to stop being completely dependent on Earth every second of the mission. Not fully independent, not permanently settled, but independent enough for long enough that the return burn could be earned on site. That is the real leap hidden inside the phrase "come home from Mars." It is not transportation alone, it is temporary planetary self-sufficiency under pressure. So the reason returning from Mars is hard is not that one piece of the mission is impossible by itself. It is that the mission is made of many difficult systems that all have to work in sequence, and each one depends on the others more than people first realise. The oxygen system depends on power. The power system depends on survival against dust and degradation. The ascent depends on preserved hardware and good timing. The rendezvous depends on ascent accuracy. The return to Earth depends on everything before it. The crew depends on all of it, and all of it depends on the crew. That is the final picture. Mars return is not one impossible thing. It is 100 difficult things that must stay good enough together, far from rescue, on a schedule set by orbital mechanics, under environmental stress, with no room for lazy assumptions. That is why getting home from Mars is hard, and that is why if it ever happens, it will mark a real change in what human civilization can do. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.